So derivatives and integrals of vector functions. So later in this chapter, we are going to use vector functions to describe the motion of planets and other objects through space. Here, we prepare the way by developing the calculus of vector functions. All right, derivatives of vector functions. So the derivatives are vector prime of a vector function R, again bold for vector, is defined in much the same way as for real valued functions. So here's the definition. All right, and this is going to be like this: d over, I changed the color. So d over dt. Yeah, this is the derivative of the R prime function. Yeah, I mean R prime vector like that. Yeah, so R with a vector on top. This equals to, well, this is, you could write it as this: R vector prime of t. This equals to now the limit. So remember in regular derivatives definition, so limit as h approaches 0 of the difference the vector r at t plus h, so minus the vector at h. So basically, yeah, you're going to subtract that difference. You can view this as rise over run, and the run is going to be h, like that. And then as the limit as approaches 0, that is our limit. That's our derivative. And of course, this definition is only if this limit actually exists. All right, so going further, the geometric significance of this definition is shown in the figure below. So if the points P and Q have position vectors r of t and r of t plus h, then the vector PQ represents the vector r of t plus h minus r of t, which can therefore be regarded as a secant vector. And I'll draw this out. So the secant vector PQ. So basically, if we have, let's say we have, let's draw this in 3D, like this. This is the x, this is the y, and there's a z. So let's say we have a curve C, like that. This is C. All right, and now what I'll do is, let's say we have a point P right here. So this is our point P, and there's the position vector to this one. This one's R of T, like that. And yeah, so you can read it over here. So if points P and Q have position vectors R of T and R of T plus H. So now if we increase the parameter T by H, so then we're going to have here, I just quickly fix that up and put a 0 there for the origin. And now let's say we had a point all the way across here. And this is our point Q now, like that. Yeah, so we have this. And now this, from P to Q, this is our position vector, PQ. That's our secant vector. And so this one right here, this is our secant vector. And that is, well, just going to be the difference between these. And this is right here for to write this. This is at R of T plus H. So now this one minus this, that's just a basic subtraction of vectors. So this equals to R of T plus H minus R of T, like that. All right, here I just quickly fix that up. And also note that it's called secant just because, remember the trigonometry, when you had a angle like this, this would be the adjacent, this would be the secant, like that. And there's the hypotenuse h there. And again, if this is the origin, and this would be the cross there. So the 0 there, so the secant PQ, so that's a secant vector there. All right, so going further, so if h is greater than 0, the scalar multiple 1 divided by h times by rt plus h minus rt. In other words, the secant vector. So 1 over h times this, it has the same direction as the r of t plus h minus rt. So in other words, the secant vector multiplied by a positive number, that's just a scalar multiple 1 divided by h, that is the same direction. So in other words, it's going to be the same direction like this. And as the secant vector, and remember that the 1 divided by h, that's just the terms of the limit right there. So basically, when you multiply by h, if it's 1 over h and it's positive, it doesn't change the direction, so it'd be the same one as this one here. And as h approaches 0, it appears that this vector approaches a vector that lies on the tangent line. Yeah, and essentially, basically, so if we have, this is the vector there, the terms of this limit right here. And then basically what they're saying that as h is going to 0, in other words, the difference between r of t and r of t plus h is negligible. So this cube is getting closer and closer and closer to this. And essentially it's going to be pointing along this tangent line. So if q was here, then the tangent line is going to be across like there. So basically this would be where the limit would be as you're approaching 0. So in other words, again, that is based on the definition there. So it appears to be approaching that tangent line as you move this Q closer and closer. In other words, the H goes 0. I'm going to erase these. I'm going to draw this better out as a separate table. I'm in a separate graph soon. So for this reason, the vector r prime of t is called the tangent vector to the curve defined by r at the point P, provided that r prime of t exists, or derivative, and that r prime of t is not equal to 0. So, and the derivative is not equal to 0 there. Yeah, so that's a tangent vector if the derivative exists and it's not equal to 0. And the tangent line to C at P, so basically the tangent line to the curve C, is defined to be the line through P parallel to the tangent vector r prime of t. So basically you draw a tangent line straight across the entire vector r prime of t. All right, so now let's draw this all out, make it more sense here. So part B, the tangent vector r prime of t. So again, that's just a derivative, it's just a tangent vector. So if I'm going to take this again, I'm going to copy this. Okay, I'm going to copy this and paste it here, and then we're going to play around with it just so we don't need to draw it out again. Put it right here. All right, so we put it there. And what I'm going to do now is I'm going to erase this. So that's just our secant vector there. And now what I'll do is I'm going to draw across here. This is going to be our the secant vector multiplied. So this right here is going to be the terms of the limit. So r of t plus h minus r of t divided by h. So it's the same direction as a secant vector, like that. And now this part right here is going to be, well, the tangent line. This is going to be if h is approaching 0. As h goes to 0, this would be the tangent line on this line right here. That's the tangent vector r prime of t. So, or in other words, the derivative. All right, and now going further, we can show this by an animation I just illustrated also. Here is a secant / tangent line animation someone made with GeoGebra. And also before we get to that, so again, the tangent line to C at P would be a line that's parallel to this tangent line. So it'd be across like this. This would be the tangent line all the way across this, and parallel to, I mean, it's going to be parallel. I was going to draw it, you have to draw it straight through it. It's going to be parallel straight to that. So that'll be the tangent line. So I'll just erase that. And I drew that just so that you don't get confused with, you don't get confused with this r of t. So these ones are typically, not necessarily parallel. So this one is going like this, and it goes to the right there. Anyways, so that's that. And I'm going to go here. Whoops, actually I meant to go here. So here's the GeoGebra. So someone made this animation, and I'll read the name out. So this is by Mukta Badari. Okay, apologies if I pronounced it wrong. So here is an animation. So this is the point P, but they have Q on the opposite side. I'm just going to move this over. I'll move P here just so it matches ours. And I'm going to pause this. I don't want to play I don't want to play the animation actually. I'll pause this. Okay, and now we can scroll up. Okay, so there it is. And zoom in. And this is our point P, point Q. And what I'll also do is go up here. So we have the A there. We can, so basically this is part of the equation there anyways. So you could, if you move this, so notice the secant vector. Here's the secant vector, and there's the parallel vector. That's terms of the limit would be straight across. That just be, so basically parallel to this one. And then as you get closer to P, it's following along this tangent line. So there's the red is the tangent line of the tangent line on the curve and this one is like a semicircle. So and then if I just go like this, it's getting closer to it, and it lines up with it. So there it is. When it's on it, it goes like that. Then going opposite, and it's always tangent. It's tangent at the point there. So at the point, it's perfectly tangent with the curve. Everywhere else is just a secant line. Notice it's extending out, and so on. And you can also move this further manually. Oh, you can't do it manually. Okay, I think they locked it up. Okay, so anyways, so that's how it looks like, and that's just the curve there. So that's just to illustrate it. As you get closer to this one, as Q gets closer to P, in other words, the h value approaches 0, then they basically coincide. So as the points P and Q are closer together, the secant and tangent lines become the same, i.e. the derivative is the instantaneous rate of change, i.e. rise over run of the curve. So in this case, there's the rise, so the difference between these two curves of the value divided by the parameter difference h there. So this one is r of t plus h minus r of t divided by this. So very similar to regular real valued derivatives. All right, and lastly, we also have occasion to consider the unit tangent vector, and that is just basically just defined as, this is as capital T of capital T vector of with the based on, or of t of the small parameter t equals to, and then this is just the derivative of the vector function like that, or of the tangent vector divided by the distance of it. So it's the unit tangent vector basically divided by the length of it, so that you have a length of 1, but then all it is just the direction of the tangent vector. So that is just, it's going to be useful later on.